Hello, in this video we're going to look at double integrals in polar coordinates. In order to go through and do double integrals in polar coordinates, we need to first review polar coordinates. So let's recall polar coordinates. From Calc 2. All right, so the idea behind a polar coordinate is that you have a polar axis, and then we have a point. The point is defined by r and theta. And to go through and get to the point, you start off by rotating theta until you're on a line, and then you go out a distance r. Okay, so to see that in action when you actually plot a point, let's say we want to go through and plot the point 2 comma pi over 6. All right, so we start off by rotating pi over 6. So to figure out where the line is for pi over 6, you can do, here's pi over 2. Then we can want to break that into thirds, and that will give us pi over 6's. So here's pi over 3. Here's pi over 6. Okay, so we want to rotate pi over 6. And we get on this line, and then from there we just want to go out 2 units on that line. So we'll say this is 2 units here. That means that this distance was 2. And that's how it works. Okay, so with that under our belt, we can then discuss translation formulas. So you can translate back and forth between rectangular and polar coordinates. So these two formulas are going from polar coordinates to rectangular coordinates, right? So if you have an r and theta, you just plug them in and out pops x. R and theta, out pops y. And then these two formulas are going from rectangular to polar. So plug in x and y, then you can get r. Plug in x and y, then you can get theta. All right, so the last thing that you need to know is some polar functions. So if any of this is unfamiliar, then you want to go through and look up a video on polar coordinates. All this information is reviewed in that. So polar functions. So we have f of theta equals r, and then we can go through and set it equal to different stuff, and we end up getting objects. Just like if you have y equals f of x, you can have r equals f of theta. So the most important polar function is if you have r equal to a constant. Right? So what is r equal to a constant? What does that produce? So if there's no theta, then just like with x and y, that means that theta could be anything. And so if we have theta could be anything and we have r equal to a number, what you could do is you could go through and plot some points to try and figure out what that is. So theta could be 0 if r is a. So if theta is 0, that's just the polar axis itself. And then we want to go a units of distance. So we could say that is a. And then if we wanted to go to pi over 6, right? So theta could be anything. So theta could be pi over 6. Then we want to go out that same distance, a. So the same distance, a, maybe right about there, about the same distance. And then if we wanted to go through, we could say, well, r would still be a, and we could have theta as pi over 3. So you want to go out that same distance again. And then r could be a and theta could be pi over 2. So we want to go that same distance again. And at a certain point, you should get some idea of what this looks like. It's going to be a circle. All right, let's see if I can manage this. Pretty good. All right. So that's one polar function that you need to be familiar with. Another polar function that you might see is r equals a sine theta. That's another one that could come up. So, and again, if all of this is really unfamiliar, you could just go and review it. So you could use the same technique that we did here. You could plug in theta values. If theta is 0, then you get 0. If theta is pi over 6, you're going to get a point somewhere over here. Pi over 3 over here. Pi over 2 over here, 2 pi over 3. So you're going to get points that are going to go like this. So they're going to end up forming a circle that is above the origin. Like that. And the center of that is at a over 2. So this distance here is a divided by 2. Right, so the diameter of the circle is a. And then you might also see r equals cosine theta. And so that is similar to the sine, the example we just did. Oop, I forgot the a. R equals a sine theta, cosine theta. Wow. R equals a cosine theta. Got it that time. Okay. And so you get the same thing, but the circle is just to the right of the origin instead of above. So here, the a sine theta, it sits above the origin. So right here's the origin. So it's sitting on top of the origin. And then here's the origin for a cosine theta. It sits to the right of the origin. And the same thing applies. This is still going to be a over 2 units. The diameter is a. The radius is a over 2. Okay, so those are most of our polar functions. So there may be others that we end up encountering. But we can discuss those when that happens. All right, so let's get into the double integral part of polar coordinates. So to go through and look at our double integral problem, we have a problem that's similar to the one that we've had in previous sections. We have a surface. We want to find the volume beneath it. All right, so here's our surface. And let's say it's z equals f of x comma y. And then this time beneath the surface, we're going to have what I'm going to call a polar base. And you'll see what I mean by that in a second. All right, so we have a starting line. That was really straight. That's like the straightest dashed line I think I've ever done using this writing tablet. That was like a miracle. Like, see, this is normal, not nearly as straight as that. That's like magic. That's incredible. All right. Anyway, so we have a starting line and an ending line, and those lines are rotations off of the x-axis. Okay, so they're not parallel to the x-axis or parallel to the y-axis. It's like you took the x-axis and you just rotated it. So what we're going to do to denote that is that this is theta equals alpha, and here is theta equals beta. All right, and then second you have a starting value inside there, and you've got an ending value. Okay, and those do not have to be perfectly smooth. Notice I did not draw them perfectly smooth. This one is r equals g1 of theta, and this one is r equals g2 of theta. And if we kind of go through and just connect, see, look how non-straight that was. See, it was so straight before. Sad. And then connect that one. So now we have a base. See, we have a base, just like the rectangle bases that we had a few sections ago, and just like the general region base that we had in the last section. All right, so what does our object look like? To figure out what our object looks like that we're finding the volume of, you just want to take the corners here and just extend them up until you hit the surface. Something like that. And then you just want to draw some surface looking curves on here to connect the dots. And there you go. That's the object that we're trying to find the volume of. So it's the volume beneath the surface, z equals f of xy, and beneath the surface and above the region of this polar shaped base, where you've got sides that are determined by rotations instead of being parallel to the x-axis or parallel to the y-axis. Okay, so how could we go through and find the volume of this? Well, the technique that we want to use is very similar to the technique that we've used in previous sections. What we're going to do is we're going to break this up into pieces, and we're going to add up those pieces. So in previous sections, we've used rectangular boxes where you had a rectangle on the base. So I would draw a little rectangle on the space like this. Yeah, I would go through and I would do something like that. All right, so we're not going to do that in this section. Okay, so this polar-based shape requires a polar-shaped base in the region. So I'll draw a bigger picture of that in just a moment, but it's not a rectangle. It's got curved edges. All right, so if you were to go through and extend that upward till it hits the top of the object, you'd get something like that. And we'll end up getting our three-dimensional object. So that's just one little piece cut out of this surface. So what we want to do is just do that a bunch of times throughout the entire object until we've chopped it all up into pieces and then add up the volume of each one of these pieces. Okay, so in order to do that, just like in the last section where we looked at general regions and just like when we had rectangles, our focus actually shifts from this three-dimensional object, this three-dimensional surface, into figuring out how to add up across the base of this. So we just ignore the z portion of it. We think about this like we're looking down the axis, down the y-axis, z-axis. So you're looking down the z-axis, what would you see? You would just see this shape and the base, and we want to think about how would we go ahead and take this shape and move it across the base? Like what would be the actual mechanics of that? So that's what we want to do next. All right, so this is going to be the picture that you'd see if you looked straight down the axis. So we have this is the x-axis here. So we're going to have a dashed line coming off of the x-axis. And then we have, this is the y-axis. So we have a dashed line that's coming up near the y-axis. Right, and then this one is going to be, this is theta equals alpha. Here's theta equals beta. And then we have a curved edge at the bottom. And we have a curved edge at the top. And then once you've done that, you can kind of connect the dots here, connect the dots here. Oh, let's try that again. I should just use a straight line. Just cheat and use the straight line tool. All right, so there's our object drawn here. And so then I can go ahead and maybe just take our little piece there. What does that piece actually look like? Let me draw it a little bigger so you can see it more clearly. So it looks like that. It has this curved edge and then straight edges on the sides. All right, so we're using that to go through and add up the, well, we're adding up the volume, but we're going to use that to kind of cover this object in so that we can go through and add up every bit of volume that's inside the base. Why this shape? Well, the side, see how the side fits up perfectly against the side, right? And then this curved edge here, it could be used to go through and add up against the curved edge that we could get from, this edge that's on the bottom, or this edge that's on the top for the top side, right? So mainly it's because we've got sharp edge on the left, sharp edge on the right. That's sharp edge on the left, sharp edge on the right, and then curved edges front and back for the curved edge in the front or the curved edge in the back. Okay, so that's the idea. Those are the shapes we're using. So how could we cover this thing? How does that work? Well, the way that it works is you go through and you actually end up using moving theta to create the slices, and then the slices go from front to back. So like this, right? So if I go through and do another dashed line, so you could think of this dashed line like I just sliced through my object, and then I'm going to take shapes that look like this, and I'm just going to draw them in, right? So I'm going to say, okay, so there's that, there's that, and you just go across the object from front to back. And by doing that, you just take this is our base, and we just, at that spot, we're finding the volume that's above that spot. That's going to be, if you took and drew this same slice on this picture, it would be like right about here. So what you'd get is you'd go through and you'd have slices like this. And above each one of those slices, we would have this, this box shape, going from the bottom of the object to the top. And I'm not going to draw because it's going to make a mess. But it will add up the volume that's directly above that. So here, just want to again be clear. We're looking straight down. So the vertical part has been chopped off. But as we go and add up each one of these, we're adding up volume, not area, because there's going to be this vertical thing that's directly above each one of these spots. Okay, so we add up a slice, and then we can add up another slice by changing theta again. And then you could go through and do, I don't know why I draw it dashed and then later on have to go through and fill it in. Just draw it filled in. And you could say, well, does this line need to match up with that line? No, because you're going to take the limit as the number of these go to infinity. All right, so this is just a representative example where I've got 9 boxes here and then another 9. Well, we're going to end up with infinity, an infinite number of these little polar shaped boxes. Okay, anyway, so you get the idea, and then you could just keep going across the object. You could do another slice, another slice, another slice, and then eventually you run out of slices. And so we're adding up in strips that go from the bottom to the top, if you want to think about it that way. Or actually, maybe a better way to think about it is from the inside to the outside. So this is the inner piece to the outer. Okay, so in order to go through and do that, what we're going to need is, if you recall from the last couple of sections, we went through and we found the area for the base, and then we multiplied by the height to get volume, right? So if you think about previous sections, let me just make this a little bit more explicit. So we would do change in x, change in y, and then above that we had the vertical to get the volume. So you had change in x, change in y times another dimension times the f of xy to get volume. So in this section, if you're going to do the equivalent for this section, then we need to be able to go through and take our shape, and we need to be able to label it like we've done here with change in x, change in y. The problem is this shape is significantly more complicated than a rectangle. How do we go through and label this? Let's figure that out. All right. So what we're going to start with is we're going to start with the area of a sector. So suppose you have a circle, and you go through and take a slice out of your circle, and we label theta, and r. So r is the radius, and theta is the size of the angle for your slice. Then at that point, the area of the sector equals, actually, let's do this. A equals 1/2 times r squared times theta. So that's the area of a sector, and that's what this is. This is called a sector. Now, if you look at the shape, let's go back. Look at the shape that we have. If you took the lines that are on the sides and you just extended them, what happens? Right, we end up with that shape. What does that look like? Well, it looks like you have, so it looks like you have a sector, right? So this looks like a sector, right? That right there. Take a look at, oops, wrong direction. It looks like this shape, like a slice of pizza. So we've got a slice of pizza, but then there's another slice of pizza. There's a big slice of pizza, and then there's a little slice of pizza where someone is like taking a bite out of the little one. You know, that took the bit the little one off of the big one. And so what we can do is we can go through and find the area of a big sector and the area of a little sector and subtract the two, and we'll get this shape. All right, so how do we do that? Suppose we've got a circle, and then inside of it we do another circle. All right, and then off the center here we do a line, and then another line. And if you look at this piece here, it should have this shape. Okay. Now to go through and label things, we're going to label the angle theta. We'll say the inner, so we've got two radiuses, I think radii. Here's R1, and then we'll say this distance is R2. So big radius and a little radius. All right, so the area for the big sector, the big piece of pizza, is going to be 1/2 R2 squared theta, right? It's 1/2 times the radius squared times theta. And then the area for the little piece of pizza that you're biting off of there is going to be 1/2 R1 squared theta. And then since we want this piece that is, you know, kind of the between the two, right? So take the big piece, then you subtract the little piece, you can just subtract the two, and that will get you this. All right. Now from there, you can go through and simplify. We could factor out 1/2 theta, and you get R2 squared minus R1 squared. And then we could factor that. And this is R2 plus R1 times R2 minus R1. Okay, so what are those things? Assuming, let's just go ahead and draw our object here again. All right, so theta is going to be the size of the angle if we just kind of extended this inward. That's theta. So if we think about the way that we go through and define the parts of our object, like change in x, change in y, we like to go through and use that type of notation. So we're going to say this is the change in theta, right? So as the number of objects increases, that change in theta will get smaller, and we'll get a thinner and thinner slice of pizza. Okay, so that's how we can control how wide the piece of pizza is this way. All right. So we're going to change that. We're going to we're going to replace theta with change in theta. All right, let's come back to R2 plus R1 because that one's a little confusing. R2 minus R1. Well, if this distance here is R2, and this distance here is R1, right? Then what happens if you subtract the two? You take the big minus the small, you get what's between the two, which is this distance here. That seems like a distance that we should have labeled with something. So let's call that change in R. That way, as the number of little pieces goes to increases, change in R, we could make change in R smaller and smaller and smaller, and it would make a thinner piece going this way. So we've got change in theta. That's kind of, you could think of that as like how wide it is, you know, on this side. Change in R, that's how wide it is this way. And then what do we do with this R2 plus R1? Okay, this is the part where it gets a little confusing. So again, so since the context that we're using this in is that we're going to take the limit as the number of these goes to infinity, and they're going to get really, really tiny. Because of that, we can go through and say something about the radius, right? So if this is the big radius R2 and this is the little radius R1, and we're going to take the limit as this change in R goes to 0, you know, gets really, really infinitesimally small, then R2 is going to approach R1, right? And so if we have R2 approaching R1, then what in effect we have is we have R1 twice. And so what we can do is we can replace R2 plus R1 with R1 twice. Now again, that's only because we're going to go through and end up taking the limit as change in R goes to 0. I don't know why I put 0 there. It's supposed to be down below. There, 0. That's going to cause R2 plus R1 to equal 2R1. All right, and so once you get to that point, the 1/2 and the 2 simplify, and this turns into R1 change in R change in theta. Okay, so that is the area for this object. And so now once we have that, so in the last couple sections, we took change in x, change in y, and we multiplied it by the function to get the volume. Now we're going to take r, change in theta, and then multiply it by the height to get the volume. All right, so it's the same idea, just a different shaped base. Change in theta, change in r, and then we're also going to throw another r on here. All right, so the area is r, change in theta. Okay, so with all that done, we can go through and actually try and get to some integrals. All right, so the problem starts in the same place as the other problems that we did in the last couple sections. So we're going to start off with some limits. So you have the limit as m and n go to infinity. And then you're going to have a couple summations. I equals 1. Hold on, actually, I want I to be the inner one. J equals 1 to m. Oh, let's try that again. I equals 1 to n. Then we're going to get f. I'm going to do something a little weird here. And then, so that's going to be the height, the z direction. That's going to be the height of my object times the base. And so the base is, area of the base is right here. So we're going to multiply by that. So we're going to get r, change in theta. Now here's the thing, right? So when we go through and label this stuff, we're going to end up moving it around. And as we move it around, just like with x and y in the previous section, we would have picked one of these corners and said it was x sub I, y sub j. Just like that, we're going to pick one of these corners and we're going to say it's r sub I, comma theta sub j. Hopefully that makes sense, right? And then we can go through and vary I and j to move across our object, right? If you've got theta already chosen, then you know, for example, if j is 1, then we're going to be getting our first strip in this direction. Then this would be this guy right here would be R1 theta 1, like right there. And then next to it, we'd have R2 theta 1. And then you'd go and you'd add up along the strip here until we get to the last one. And the very last one is going to be, and it doesn't really matter where you put the point, but it's going to be R sub n theta sub 1. And then when you're done with that, you increment theta to 2 and you do it all over again. Then increment theta to 3, another strip. Keep doing it until you get to the last theta value, and then you'll have theta sub m all the way from R1 to Rn. Okay. So all of that was to basically say that you should put an R sub I there. Okay. Now F, this is the part that's going to be a little strange. What is F? F is in terms of X and Y, right? See how it says Z equals F of X, Y. So we have a function F, X and Y, not a function of R's and thetas. We need to convert this. All of the variables we're using are all R's and thetas. So how do we convert from X and Y to theta and R? Sorry to keep going back and forth. But if we have to go back to the first page, how do we convert from X and Y to R's and thetas? We got two formulas right here. So we're just going to go through and use those. All right, so we just pop those in. And then this gets me my integral. Or not my integral, sorry, my Riemann sum, my limit sum. And so the next thing that you do from there is very similar. Actually, hold on, let's do a little bit more before we just jump right to the integral. So as far as how we're going to define things, so we want theta to be the outer integral, or the outer summation, outer summation, because of the way that we did those strips, right? So we picked theta first. One more time, back to the image. We picked theta first, and then we varied R. Then we incremented theta, then varied R. Incremented theta, so theta gets chosen first, and then R varies. So that's why the outer sum is theta, and the inner sum is R. And so also because of that, in terms of choosing our values, so theta is going to be beta minus alpha over m, and then theta sub j is going to be alpha plus change in theta times j. Meanwhile, when it comes to R, we're going to have change in R. Change in R, I lied one more time. Change in R, R is going to go from the front, or from the inner piece to the outer piece. The inner piece to the outer piece. So the inner piece is defined by G1 theta, and the outer piece is defined by G2 theta. So we're going to have G2 theta minus G1 theta divided by n. And then R sub I is going to equal G1 of theta plus change in R times I. Okay, so once you've done all that, the rest of this double integral, double summation, plays out exactly the same way as the example that we did in the last video with the general region. This is all general region type stuff. It's just that we've got change in theta instead of change in x, and change in r instead of change in y, but those are just letters. Once you have all of this written out, you can go through and just say, hey, I'm just going to take all the stuff that I did in the last derivation and I'm going to use it on this derivation. All right, so how does that work? We can just pop in some integrals here. All right, and then we're going to have f, and we'll have r sub i's become r's, theta sub j's become thetas. All right, we're going to have r's and sine theta here, and then r sub I becomes r, and then change in r, change in theta, that becomes dr, d theta. Okay, and then the bounds here, the outer bounds come from the variable that was chosen first. We said theta was chosen first, so we should have theta equals alpha to theta equals beta. And then the inner bounds are dependent upon, or, well, they're all that's left, which is are going to be the R bounds. And we can see they go from G1 of theta to G2 of theta. Okay, and so that gives us a nice handy formula for going through and finding the volume that's under a surface that's above a polar region. Okay. Now, we'll explain the r cosine theta and r sine theta in a few minutes, but the next thing that we need to explain, because this is going to be a critical part of going through and doing problems, is that most of the problems you're going to start with are going to start with x's and y's, and you're going to go through and decide to change them and interpret the problem differently. You're going to decide to use r's and thetas instead. Okay, so the idea behind that is that, you know, because you could go through and evaluate the volume this way, you could also go through and evaluate the problem, you know, using a general region. What we're going to get is we're going to get two formulas, right? So, well, two formulas. Well, it's one formula in effect, but what we could do is we could go through, right, and you could calculate the volume using a general region. If you did that, you'd get double integral f of xy dA over d or r, or whatever you want to call it. Or you could calculate the volume using polar. And if you did that, you'd get a double integral. You get f of r cosine theta, r sine theta, r dr d theta, you know, from g1 theta to g2 theta, and from alpha to beta. So given an object, given a volume, you could go through and you could calculate it this way, or you could calculate it this way. Well, if I go back to for the millionth time to this picture, if I calculate this using a general region, I find the volume that's inside here. Yep, I got this weird polar shape, but I find a way to do it. I go through and I use the technique from the previous section, and I just calculate it using a type 1 or a type 2 general region. Or I go through and I use my polar, all my polar stuff. I go through and I calculate it using polar. What do you think would happen to those two volumes? If you calculated it two different ways, what should happen? They should be the same. Okay. And so this result that we just created by thinking about the problem that way, this is what we're going to call the conversion formula. It's going to enable us to convert from the rectangular coordinates over into the polar coordinates. And when you're going through and doing problems, the problems are almost always going to start with rectangular coordinates, and then you'll want to do a conversion. So this formula is just as important as the one that's above that came out of the derivation. So we're going to use this one a lot. Okay, and so this is, we're going to call this the conversion from rectangular to polar formula. This is our conversion formula. Okay, so how do you go through and use the conversion formula? Let's talk about that on the next page here. So let's say we start off, we've got a problem. They give us the problem. They say, go through, find this. And they describe D. So they say, D is, whatever. You've got some description for D over here. So they give you this, and they give you the function, of course, too. So they give you the function, and they give you D, and that's it. That's what we did in the previous section. You've got to figure out the order of integration here. So they give you a function, they give you D, and they say, go to town. And so you decide, you know what, I want to use polar coordinates. Why would you use polar coordinates? Well, we'll cover that a little bit later in the video. All right, so what we can do is step one, you're going to convert f of xy from rectangular coordinates to polar coordinates. How do you do that? All right, so to do that, you're going to use the translation formulas. And the way to represent using the translation formulas, what we're going to do is we're going to rewrite this, and we're going to use the translation formulas. We're going to plug into it, and so we're going to get f of r cosine theta, r sine theta. Okay, so that's what this represents. This represents, you can keep going. Oh, hold on. Yeah, so that's what this represents, and this represents. Well, there was more to it than that. And so that's what the f of r cosine theta, r sine theta represents. It represents the fact that you started with f of xy and you converted it into r's and thetas. All right, so that's step one. Actually, let me move this closer. Then step two, you're going to convert dA into the polar equivalent. What is the polar equivalent of dA? It's r dr d theta. And then finally, you're going to convert D from rectangular to polar coordinates. And that one's going to be the hardest of the three. Okay, so all that said, let's actually go through and try doing a problem so we can see how involved this is. So the instructions are to evaluate the integral by changing to polar coordinates. And the integral we're given is the integral, you're told to integrate across the base D. You've got x dA, and they say D is the right half of the disk with center at the origin and radius 3. Okay, so what we can do here first, before we don't even need to think about D just yet. You can go and you can just translate everything. All right, so what is x in polar coordinates? It's r cosine theta. What is dA in polar coordinates? It's r dr d theta. And then we're left with figuring out what the bounds are, and we know they go from r to r and theta to theta. Okay, so to figure out this part, it's just like the problems in the previous section with general regions. You need to sketch the D that they gave you, right? You need to go through and graph it. All right, so what are you told? You're told that it's the right half of the disk with center at the origin. So by disk, they just mean circle. So it's this, the right half. Okay, so what we need to figure out is we need to go through and figure out what the bounds are going to be for this polar shaped object, right? So, and the way to do that, you know, for your first problem, so the R, this bottom R, so I talked about it when we you know, multiple times when we were looking at this picture, it goes from the inner piece to the outer piece. So what you want to do is you want to do the inner radius to the outer radius. That's the R values you want. So the inner radius to the outer radius. If you look at this object, right, the outer radius is easy to figure out. It's going to be where the object stops. All right, so this outer radius, what's this outer distance? Well, you're told it's 3. What is the inner distance? If this goes all the way to the origin, then the inner radius is going to be 0. There is no inner radius. It fills in all the way to the center. All right, and then for theta, so if this is 0, then this way we would have negative theta. So we would go from negative pi over 2 up to pi over 2. All right, and that's our integral, and that's how you set it up. All right, so when you're given a rectangular double integral, to change it into a polar, you want to take the x's and y's and use your translation formulas to get rid of them. Replace the dA with r dr d theta. Sketch the base, sketch the object that you're integrating across, and then figure out how to go through and describe that in terms of the bounds. All right, so we can go through and do this integral real quick. This is negative pi over 2 to pi over 2. This is going to be r squared. So I'm just going to go ahead and do this in one step. This is r squared dr. So the antiderivative is going to be r cubed over 3. 0 to 3. And then you're still going to have a cos theta hanging out in there. D theta. And then if you plug that in, you're going to get 27 over 3. That's 9 minus 0. So we're going to get 9 integrals, negative pi over 2 to pi over 2, cos theta, d theta. And the antiderivative is going to be 9 sine theta, negative pi over 2, pi over 2. So it's going to be 9 times. And then if you plug in sine of pi over 2, that's 1 minus sine of negative pi over 2. That's negative 1. So we're going to get 1 minus negative 1. That's going to give us 18. Okay. Let's try another example. Same instructions. You're given an integral. D is the region between the circles. X squared plus y squared equals 1. And x squared plus y squared equals 9. All right. So first thing you can do, you don't even need to think about D just yet. You can go ahead and change this. So x squared plus y squared, what is that in terms of our translation formulas? If you go back all the way to the beginning, x squared plus y squared equals r squared. So we can just pop in an r squared. And then dA is r dr d theta. And what's left is we need to figure out what the bounds would be, r to r and theta to theta. To do that, you need to sketch the object. And what does the object look like? So it's the region between circles. So you have, here's a circle. Here's another circle. Right, these are not going to be to scale. But we're going to say that this inner radius is 1, and this inner radius, then the outer radius here is 3. Okay, so if we're going to go through and add up what's between the two, we want to go from inner radius to outer radius. So we're going from inside to outside, inside to outside, inside to outside, all the way across the bottom, the object. You just keep going inside to outside. So what does that mean for R, the bottom R, which is the inner radius? All right, it's going to be that from the inner circle. So that's going to be R equals 1. And then the outer radius is going to be the other one, 3. And so as far as theta is concerned, when do we start counting area and when do we stop? Well, we start at 0, and then we go to pi over 2, go to pi, go to 3 pi over 2. We just keep going until we all come all the way around back to 2 pi. Okay, and then from there to go through and evaluate the integral, this is a fairly simple u substitution. U equals e to the r squared. Hold on, not e to the r squared. That is a Calc 1 student mistake. U equals r squared, du equals 2r dr, throw in a 2, offset it with a 1/2, and we get the integral 1/2, the integral from 0 to 2 pi, and then 1 9 e to the u du d theta. So this equals 1/2 0 to 2 pi e to the u, evaluated 1 to 9, 1/2, integral from 0 to 2 pi. This is e to the 9 minus e to the 1. There should be a du there. Oh wait, no, there shouldn't. Oh, I'm so accustomed to forgetting to put that. Here's where there should be a d. There's a d theta. And then, so the antiderivative of this is going to be theta, and then you plug in 2 pi and 0, and you get 2 pi. So we get e to the 9 minus e to the 1 times 2 pi. 2's cancel, and we get e to the 9 minus e times pi. All right, so that's 2 examples. Now, the next type of problem are the type that we did also in the last video, and that is going through and finding the volume of a solid, the volume. So these are significantly harder problems. Well, you say, what were we just doing if we weren't finding volume? We were finding, in the last problem, we weren't, I guess the result of this is a volume, but we were just given a problem and told to evaluate. This is different, where they're going to describe an object and they're going to ask us to find the volume. So find the volume of the solid below the cone z equals the square root of x squared plus y squared, and above the part of the disk x squared plus y squared is less than or equal to 4 in the first quadrant. Okay, so one of the things that I talked about in the last video is that if you parse these problems really carefully, you can tell how much graphing you need to do, like how good an idea you need to have of the object to figure out, what the region of integration is going to be. If the problem describes the base to you, then you don't need to go through and graph the object. You could just use the base that was described. And so if you read this, find the volume beneath a thing and above above something. So if it says above something, well, then they've given you all the information that you need about the base. The base is written right here. And so you don't need to go through and sketch the object because they've described the base to you. Okay. If you want to, you could go through and graph the cone. But in this problem, because of the fact that they have described it in the way that they have, this is not going to be part of the base. The base is entirely described in the problem. If the language had been something like find the volume of the solid bounded by z equals this and z equals something else, then that's an entirely different problem. In that problem, they have not described the base. They haven't said above something. You have to go through and figure out what it's above. Okay, and this is an easier problem because of the fact that they have this piece here and above. We can go through and rely upon that to go through and do our integration. All right, so with these problems, this is what I recommend that you do is you go ahead and you first start by writing the integral, and we're just going to use rectangular coordinates. We're going to translate over to polar. So we're going to start with rectangular. And so if you're finding the volume that's beneath something and above something else, the thing that it's beneath, that's our f of xy. So we're going to start with the square root of x squared plus y squared. And then you have dA and then over d. And this is the region D right here. They gave it to us. Once you've done that, now we can translate over to polar coordinates. So x squared plus y squared is r squared. dA is r dr d theta. And then d. Now's the hard part. All right, so we got to go through and figure out what the base is. We've done all the easy stuff. To figure out what the base is, what you need to do is you need to graph it. So we can go through and we can draw a coordinate axis. The problem says it's the part of the disk in the first quadrant. All right, well, what is the disk? This is a circle, a filled in circle. So we've got radius 2. And it looks something like that. All right. And then we're told it's just in the first quadrant. So I only drew one in the first quadrant, but this is second quadrant, third, and fourth. So I just did the part that's in the first quadrant. All right. So looking at that, how could we go through and describe that using polar coordinates? We want to go from inner radius to outer radius. So there is no clear inner radius because it goes all the way to the origin. When that happens, r is 0. And the outer radius, well, we marked it there a couple times. That goes until we get to 2. So you can go through and adding up the object by doing that. And then theta, well, so theta equals 0. This is the polar axis right here. So we want to start, right it there, write that value. And then we want to stop when we get to this line here. And that is denoted by theta equals pi over 2. Right, and that's it. Okay, that's all you need to do to go through and set up the integral. To evaluate it, you have 0 to pi over 2. This is going to be 0 to 2. It simplifies root r squared is r times r. So we're going to get r squared dr d theta. Here you get 0 to pi over 2. The antiderivative is r cubed over 3. 0 to 2 d theta. So we're going to get 0 to pi over 2. Plug in 2, you get 8/3 minus 0. So we're going to get 8/3 d theta. And then the antiderivative of this is going to be theta. And you're going to plug in pi over 2. So we're going to get 8/3 times pi over 2. Right? That simplifies. You've got 4 and 1. And so we're going to get 4 pi over 3. All right, there's another example. And then finally, let's try a little bit harder one. This is one of those ones where you're going to need to sketch the object. All right, so you're told to go through and find the volume of the solid bounded by z equals x squared plus y squared and z equals 4 minus x squared minus y squared. Okay, so this again goes back to the previous video. We discussed these problems where it's not crystal clear what the base is because it's not described. So I like to go through and draw them in 3 dimensions, but lots of people like to go through and just try and do 2. So I'll try and show you how to do the problem with just 2. But I encourage you to try doing it with 3 because I don't think these are especially difficult things to graph. All right, so we've got our z-axis, x-axis, and y-axis. This is a paraboloid opening upward. This is a paraboloid opening downward. Oof, that last one was really bad. Those all were pretty bad, actually. Those did not do a very good job drawing the second paraboloid. So what we got here, 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 and here. It's not that bad. All right, so you're gonna get this. You're gonna get that butchery looking circle there. Let me erase that and try that again. Oh wow, wow. Here we go. Slow. We got this. We got this. All right. And so what it looks like is you got a bottom paraboloid, a top paraboloid, and they're meeting at this circle. So if you go into your kitchen and take a bowl and hold it so that one part's opening up, and you hold another bowl, well, one part's opening down, that's your object that we're asked to go through and find the volume of. Now, that's what you've got to do if you want to, just be able to recognize it. What you could do, what sometimes people do, is they'll go through and they don't like graphing the objects, and so they could go through. What could they go through and do this? So they could go through and they could look at this. You would have to recognize at minimum that this is a paraboloid and that it is opening upward, and this is a paraboloid and it is opening downward. And at that point, you could just recognize, hey, I've got one opening up, one opening down. They're clearly going to intersect. How could I find the intersection? Well, I could go through and set the z's equal. So you could do x squared plus y squared equals 4 minus x squared plus y squared. And then if you do that, you'll get 2x squared plus 2y squared equals 4. And then you'll get x squared plus y squared equals 2. Right? And that is the circle of radius root 2. What is that on this picture? That's this circle. Let me try coloring it in red here. That's this circle here. This distance here is the square root of 2. Okay, and so the three-dimensional picture just gives you a bit more context, a bit more flavor, but you can get to the same place, without it. All right, now there's one more thing that you do need to be able to figure out, if you don't want to graph it in 3 dimensions when you graph it here. You got to figure out which one's the top and which one's the bottom. I'll explain why in a second, but you've got to look at this one and say, okay, that's a parabola opening up, that's a parabola opening down, so this one is the top, and this one is the bottom. Assuming you could do all that without the picture, then you're actually okay. All right, so how do we go through and set up the integral now? We have double integral. Now here is where we put the function. Okay, so what is the function? The function, so the function is usually we're finding the volume under something. Under something. Now, it's very difficult to tell looking at this picture, you know, what's going on. But looking at this picture, under something, we have a top surface, this top bowl. If you go under that, what happens? So let's just pick a spot and go under it. Let's use a different color than black. Let's pick a spot here, and then we're going to go under. So you start going downward. What happens? Boom. You hit the bottom bowl, right? You got a top bowl and you've got a bottom bowl. So because of that, we're finding the volume that's under this top surface and above this bottom surface. We want the volume that's between the two surfaces. How do we find the volume between two things? We subtract them. So what we want to do is you want to take 4 minus x squared minus y squared. That's the top. And then do minus x squared plus y squared. That's the bottom. And this here, this is the top surface minus the bottom surface. That gets us the volume between the surfaces. All right, and then we can rewrite this, and then we're just going to leave this d and leave this dA. You can rewrite this. This is 4 minus 2x squared minus 2y squared dA and d. All right, and let's go to the next page here. So once you've gotten that far, you can go through and change over to polar coordinates. So we're going to go from 4 minus 2x squared minus 2y squared to 4 minus r squared. And then dA is r dr d theta. And then we just need r bounds, and then we'll be in business. So the inner radius, if we look at our object, the inner radius, there is no inner radius, right? It goes all the way to the center. So if it goes all the way to the center, then we want the inner radius to be 0, then root 2. And then for theta, we start at 0 and go all the way around. So you get 0 to 2 pi. And then from there, to go through and evaluate that, we do 0, 2 pi, 0, root 2. This is 4r minus r cubed dr d theta. Then 0 to 2 pi. This is 2r squared minus r to the 4th over 4. 0 to the square root of 2 d theta. And we get 0 to 2 pi. You could plug in 2. Root 2 times root 2 is 2 times 2 is 4 minus root 2 times root 2 is 2 times root 2 times root 2. Wait, what? Oh, sorry. I forgot about the 4 in the denominator there. I was like, wait, that's 4 too. Well, maybe the volume is 0. That doesn't seem possible. All right, so yeah, so we get 2 times 2 is 4. 2 times 2 is 4 over 4. And so that gives us the integral from 0 to 2 pi of 3 d theta, which is going to be 3 times 2 theta. That's going to be 6 theta. Okay, hold on. Did we do that right? So we multiply the 4r, r cubed, 2r squared, r to the 4th over 4. I got it all discombobulated. Yep, looks good. All right, so that concludes the video. That's how you handle polar coordinates. And let me say one more thing actually about double integrals over polar coordinates. So you notice how in all these problems we ended up having circles. So that's the thing that's going to live on beyond this section, beyond this video. In future sections, anytime we encounter a double integral or we're going to introduce triple integrals in a next. Anytime that we have that happen, if the circle, if we have the circle, there's if the base is in the shape of a circle or part of a circle, we're going to break out polar coordinates to do it, because polar coordinates handle circles a lot better than rectangular coordinates. Okay, so that's just the one little extra tidbit, is that this material does live on in future sections. All right, well, thank you for watching. See you next time.